Okay, so our next test, as you know, is next Tuesday. It's going to be on sections 8.2 through 8.5. There are 6 problems, and so there'll be 1 integration by parts, 1 trig integration, maybe 7, 6. Let me think about that. 1 integration by parts, 2 trig integrations, 1 involving sine and cosine, 1 involving secant and tangent, 2 partial fractions, 1 involving distinct linear factors and 1 involving a linear factor and a quadratic factor, and a trig substitution problem. So the review is posted online. I sent you an email. And I made up the test yesterday. I was working through it. I haven't finished it yet. Not that it takes that long. I just had to go do something else. One thing, I mean, it's not, well, yeah, that's debatable. But I was going to work on one problem, and I may have worked it in the review, but I'm going to work again just to remind you of something, because there are going to be things like, for example, integration by parts, where you might have something like x times e to the 3x dx. So you got to know how to deal with when you have an exponent that's not just x, or you might have something that's like x times the cosine of x over 2 dx. And remember where that comes into play is when you say you let dy you let dv equal cosine of x over 2 dx. When you integrate that, so to get v, you integrate cosine of x over 2 dx. So you have to use u substitution. U is x over 2. Well, there's 2 ways of doing it. You can use u substitution. So you got u is x over 2, so du is equal to 1/2 dx. But the substitution I have is dx. So you get dx is equal to 2 du. So you multiply both sides by 2. So when you actually integrate this, you'll have the cosine of u times 2 du. So the 2 comes out. The integral of the cosine is the sine. And then you plug it back in, plug u back in, so you get 2 times the sine of x over 2. Okay, so that's the integration. The other way that I've told you about is when you have an argument of a trig function or an exponential function, you divide by the constant that it's multiplied by. So if you look at this as the cosine of 1/2 x, which is the same thing, all I'm doing is just separating the 1/2 out. When you integrate this, you just divide by the coefficient, and then you integrate. Integral of the sine is the cosine. The argument doesn't change, so it's still 1/2 x. So you end up with 2 sine of 1/2 x. That's the short way to do it, which is fine. If you want to use the whole u substitution thing, you can go through that. So if I have v is equal to the integral of e to the 4x dx, the answer is going to be equal to 1/4 e to the 4x. So don't forget to do this part, and don't change the argument. Okay. So when you integrate, you divide by the coefficient in front of the exponent. If I took the derivative with respect to x of e to the 3x, the answer would be 3 e to the 3x. There I'm using the chain rule. So when you differentiate, you get 3. It's just like here when I didn't, not there, but so here the exponent is 3x. The coefficient in front of the exponent is 3. So when you take the derivative, you multiply by that. Again, you could use the chain rule. F of u would be e to the u, and u of x would be 3x. So u prime would be 3, and then you do it the long way. But the easy way to do it, we've been doing it so long, there's no point in going through this long thing. When you take the derivative, you multiply it by the coefficient in the exponent if it's just x by itself. If you integrate, you divide by the coefficient in front of the argument. Okay, and that happens a lot on the test, so just make sure you know how to do that, or you're going to lose. I mean, it's not like you're going to fail the test, but you might get everything else right and mess that up, and you'll end up with a B instead of an A. Another example of something like that would be in terms of trig integration. So let's say we have, let me think about this. Tangent squared of 4x times the secant squared of 4x dx. So you have to do the same kind of thing. In this case, you would let you. In this case, I've already separated the part that's going to be du. This part's du. So u is equal to the tangent of 4x. So this part is u squared. And then if I take du, what I'll get is 4 times the secant squared of 4x. So again, because I have this constant multiplied by x, when I take the derivative, the chain rule says that I take this coefficient and multiply it by the derivative of this. The derivative of the tangent is the secant squared. The argument stays the same. So when I make my substitutions, I've got secant squared dx. Here I've got 4 secant squared dx. So I'd put secant squared 4x, I forgot my dx here, sorry. Dx is equal to du divided by 4. So if I make the substitution, I'll have u squared, tangent squared, times secant squared 4x dx, which is going to be du over 4. So I get 1/4 the integral of u squared du, which is u to the cubed over 3, plus c. So a lot of people, what they would do is they would just integrate this and say they forget the 4. So don't forget this part. Almost every problem has, well, not maybe, at least half the problems have something where the argument of the trig functions or the exponent is something other than x. In the trig integration problem, I'm going to give you some hints, because it's not that it's super hard, it's just that you guys are just not, most of you are not great with trig identities. And the only way you get good with trig identities is to do them all the time. And we just don't do them enough to be good. Nate last year, he was the king of trig identities. He seemed to, for some reason, that was his talent. He knew what he was doing. Okay, so what we were doing yesterday was we were talking about telescoping series, and I said that this is probably going to equal to that, but I'm not sure. So what we have to do is we have to use partial fractions to figure out what the two coefficients are to break this into two fractions instead of one fraction. So remember, what we do is when we have two linear terms, basically, they're linear terms relative to infinite series, but you'll get a times n minus 1 plus b times n plus 1. That's equal to 1. So this times that plus that times that. And this is the case where we let n equal 1 and we let n equal -1 to make these two terms drop out. So if I let n equals 1, I'm going to have a times 0 plus b times 1 plus 1. So you get b is equal to 1/2. You get 2b is equal to 1. And over here you get 1 is equal to a times -1 minus 1 plus b times 0. So you get a is equal to negative 1/2. So I guess that's pretty close. Not exactly right. So this original series can be broken down into the summation from n equals 2 to infinity of, I'm going to put the positive one first. So it's going to be 1/2 times 1 over n minus 1 minus 1/2 times 1 over n plus 1. Now what we'll do is we'll just make up a table and look at it and see what happens. We'll show you why it's called a telescoping series. So let's say this is n, and this is going to be a sub n. So we start at n equals 2, 3, 4, 5. So what we're going to have is 1/2 times 1 over 2 minus 1 minus 1 over 2 times 1 over 2 plus 1, plus 1. And I'm going to move these down because I'm not having enough space to finish this calculation. So we'll have 1/2 times 1 over 1, okay, minus, so we have 1/2 times 1/3, so that's going to be 1/6. So the first term is 1/2. I just write that up. So the first term is 1/2. The second part's 1/6. Now when you let n equal 3, you're going to have 1/2 times 1 over 3 minus 1 minus 1/2 times 1 over 3 plus 1. Again, I'm going to move these down so I can. So that's going to be 1/2 times 1/2, which is 1/4. And then here we have 1/2 times 1/8, or 1/2 times 1/4, so that's going to be 1/8. Doesn't look like things are working out perfect yet, but they will, don't worry. So the next one is 1/2 times 1 over 4 minus 1 minus 1/2 times 1 over 4 plus 1. So 1/2 times 1/3 is 1/6. And here we have 1/2 times 1/5, which is 1/10. You can kind of see what the pattern is now. We don't even have to, once you've kind of figured out what's going on. So the next one will be, this is 1/2, 1/4, 1/6. This will be 1/8. And this goes 6, 8, 10, 12. So this is minus 1/2. 1/12. And so each subsequent term is going to be like that. So if we put them all up here, so we have 1/2 minus a 6. That's the first term. And then we add the second term, which is 1/4 minus 1/8. And then we have 1/6 minus 1/10. And then we have 1/8 minus 1/12. So this cancels out with that. This cancels out with that. And so ultimately what happens, everything gets canceled out, and the last term, except for the last term, which turns out to be 0. So the last term is going to be 1 over infinity. That's the only one that's left over, which is 0. So the only two parts that contribute to the actual sum is 1/2 plus 1/4, which is 3/4. So that's the answer. So initially, for one thing, it doesn't, you wouldn't necessarily see this as a telescoping series. When you have a telescoping series, you always have one term that's positive and one term that's negative, and the parts are such that they repeat each other as n gets larger. So here 1/6 repeated here with 1/6, but this one happened in the second term, this happened in the first term, so one's negative and one's positive, and they cancel out. So that's a telescoping series. And that's how you figure out what the answer is. Now I'm actually just going to do this in an Excel spreadsheet just to show you. So we're going to have n, and we're going to have a sub n. So here's a sub n. Here's the sum. So these are going to be the nth partial sums. We're going to start at 2, 3, 4. We'll do 51 terms. And the terms, and I'm going to use the original expression, not the one not the one that I broke apart. So it's 1 over n plus 1, n minus 1. Okay. So that's going to be equal to 1 divided by n plus 1 times, we got to divide again, divided by n minus 1. So that's the first term, 0.33. And the sum is initially just going to be the first number. So now if I copy this for the second term, it's 0.125. And then the sum is going to be the previous number plus the new number. And I get that. Now let's just go back and check to make sure that first term. So if you take 1/2 minus 1/6, you get 1/3, which agrees with what I have here. Okay, so I feel pretty confident I did it right. And now that I have an equation for this cell and I have an equation for this cell, which depend upon values that I've already put in, I can just copy these equations down, and you can see that each term gets smaller. So it's satisfying the requirement that the nth term is going to go to 0. It doesn't go that fast, and that's one reason why this thing doesn't. The answer was 0.75, it was 3/4. But even after 51 terms, we're still not there. You'd have to go. Let's see how far you'd have to go out to get really close to 0.75. Some series converge very quickly, and some do not. So I'm going to go out to 565 terms. We'll see how. Yeah. It's taken a long time to get to 0.75. But now you can see why, because the terms are getting really small here. Anyway. Okay, so that's one we just did. So since you guys have to do partial fractions for the test, why don't you use this as a practice? So what you're going to do is you're going to take that fraction and you're going to make it into two fractions, a over 2n plus 1 and b over 2n plus 3. So you need to solve for a and b. And once we do that, then we can look at the terms. And while you're actually working on that, I'm going to go to my office and get my book for a second. I need to, so that'll give you enough time to hopefully get that finished. So the reason I was getting my book is I was curious if there was a formula for what the actual sum was without writing it out like we just did in the previous problem. And it is, but I'm not sure what I know what it means relative to what we just did. So we'll just stick with, I'll have to look at that. Okay, so let's see what we get. It's not quite as simple, is it? Because it's not a linear factor, but it shouldn't be that much more. So you could say, in this case, to make that go to 0, you'd let n equal negative 3/2, I think, right? And to make this go to 0, you'd let n equal negative 1/2. So if you multiply 2 times this, you get 6 halves, which is 3, negative 3, so that works. Yeah. Okay. So you get 1 is equal to a times 0 plus b times 2 times negative 3/2 plus 1. 1 is equal to, so that's going to be negative 3 plus 1. So you get negative 2b. B equals negative 1/2. You do the same thing up here. So you'd let the second term goes to 0. So you get 2 times negative 1/2 plus 3 plus b times 0. So that would be 1 is equal to a times, this is going to be negative 1 plus 3 is going to be 2. So you get a is equal to 1/2, positive 1/2. Okay, that makes sense. Right there. So our original series is the summation from n equals 1 to infinity of, which one was positive? A. So it's going to be 1/2 times 1 over 2n plus 1 minus 1/2 times 1 over 2n plus 3. So that's the telescoping series. And so you could plug in the values of n starting in this case at 1. The reason it starts at 1 is we couldn't use 2 before. I mean, we couldn't use 1 in the previous example because it would make the denominator go to 0, which wouldn't work out too well. So here's a sub n. So you're going to end up with 1/2 times 1 over 3, so 1/3. And then you're going to subtract 1/2 times, when you plug 1 in, you'll have 2 plus 3, which is 5. So you get 1/5. So that's the first term. And the second term is going to be 1/2. 2, you get 2 times 2 is 4, plus 1 is 5. So you get 5. And then the next one, you plug in 1 here. So you get 2 times 1. Did I do something wrong here? Oh, 2. Stick 2 and you get 2 times 2 is 4, plus 3 is 7. So you get 1/7. And continuing on, now you can see the pattern. You're going to have 1/2 times 1/7 minus 1/2 times 1/9. And that goes down. And so in this case, these cancel out. The only term that actually ends up surviving is the first one. So the answer to this question is equal to 1/2 times 1/3, which is 1/6. Okay. So this is asking for the convergence of this one. And again, the only kinds that we've looked at so far, well, there's the nth term test. So we always should do that first. Does a sub n go to 0 when n goes to infinity? And the answer is right, because you've got, as long as that ratio is between 0 and 1, it's going to be a fraction. Anytime you raise a fraction to a very high power, it goes to 0. So you can't initially say it's going to diverge. And then the second, it's not a telescoping series, it's a geometric series. And so once you recognize it's a geometric series, you ask the question, is R between 0 and 1? And the answer is yes. And the rule says it converges. Okay, so what we would say, let's go back to the rule, just so we know what it said. Again, you'll have a piece of paper that has all these rules on it. You just have to apply them. And I've done them now enough that I remember most of them, but here's the rule. A geometric series with the ratio R diverges if the absolute value of R is greater than or equal to 1. If the absolute value of R is between 0 and 1, then the series converges. And it converges to this value, a over 1 minus r. So probably the best thing to do is, well, I'm just going to drag this thing so I can look at it when I'm trying to answer the question. If I can find it. I think that's it. No. One more, I think. Where's my problem here? Oh well. So what I would say is, since this is a geometric series and the absolute value of R is between 0 and 1, the series converges. So the actual series value is going to be equal to a over 1 minus r. I think that's what it was. Gotta find my formula. I don't remember these things. Where is it? Where's my rule? I've lost it. Oh, there it is. A over 1 minus r. Okay. So that's the rule. Go. So in our case, a is 1 because there's no coefficient in front. So it's going to be 1 over 1 minus a negative 1/2. So that's 1 over negative 1/2 times a negative sign gives you positive 1/2. 1 plus 1/2 is 3/2. So the answer is 2/3. So that's what the geometric series converges to. Let's actually just look at that series too. This is 1/2, negative 1/2 to the n. So I'm going to do my Excel spreadsheet. Do a new spreadsheet here. Just show you how it works. Prove that the formula works. And so what you'd have is n, a sub n, and the sum. And we'll start with 0, 1, 2, 3, 4. I guess I didn't. This one actually converges pretty quickly, I think. I'm just going to do 14 terms. So a sub n is equal to negative 1/2 raised to the n power. So the sum initially is the initial value. I can copy this thing to the next line. So that's the second term. This is going to be equal to the previous term plus the new term. And then I can just copy these. And you can see it's going to alternate because of the -1 raised. When it's an even power, it'll be positive. When it's an odd power, it'll be negative. And you can see that after 14 terms, that the nth partial sum is 0.666687. And we said theoretically, well, not theoretically, it's not theoretical, it's real, was 2/3. So here it converges much more quickly to the answer. So that confirms that we're apparently doing something right. Okay. Now sometimes you're given the series as a sum and you have to figure out what the equation is. So again, this one looks like it's going to be something 3 to some power, say 3 to the n power, divided by 2 to the n power. Just because I'm getting 9, 27, 81, so that's the powers of 3. And here we get 2. Well, actually, that looks like it might be, what would that be? That might be something like 2 to the, this is the first power, this is third power. So how would you do that? You might do something like 2n minus 1, maybe. Let's see if that makes sense. So, what I was, let's say this is n equals 0, 1, 2. So 2 squared would be 3. If you had 2, you'd have 2 times 2 is 4, minus 1 is 3, 2 cubed. So that would work out. The problem is I think the next one's not going to work out quite as well. If you have 3, you're going to have 3 cubed, which is 27, divided by 2. Well, that one's going to work too. The question is, what does it do when it's 1? So if you have 3 to the first power, and you divide by 2 times 2 minus 1, that doesn't work out. Okay. So it worked for 2 out of the 4, but it's not working for the other ones. Let's look at it as a geometric. Let's do it 3 over 2 to some power of n. And then multiply it by some constant. So let's see how far we're off. So if we let n equal 2, we're going to have 3 squared over 2 squared. So if I multiply it by 2, so if I had 2 times this, I'd have 9, and then I have 2 divided by 2 squared, which would that would work out. So that's another option. Let's try it for the next case. Let's look at n equals 3 using this formula now. So you'd have 2 times 3 squared over 3 cubed over 2 cubed. That doesn't work out quite right either. Okay. Rats. It's Friday. I'm going to have to think about this one. I'm not going to put something like that on the test, so we'll come back to that. And the last example that we're going to look at is this one. And it's not a telescoping series. It's not a geometric series. So kind of by default, you might say, well, the only thing we have left is the nth term test. And you can see that you can apply that because as you let n go to infinity, so if I take the limit of the term in the summation as n goes to infinity of n plus 10 over 10n plus 1, the answer is going to be 1/10. And that's because use the leading coefficient rule, 1 over 10. These are the highest order terms. And so since the limit of a sub n as n goes to infinity does not equal 0, the series diverges according to the nth term test. Okay. By the way, did anybody figure what this is? What the right solution is? Okay. And I gave that the other day, so if there's anybody here today that wasn't here the other day, there's the assignment for 9.2. So we're going to move on to 9.3, some new convergence tests. Unfortunately, we've got to slog through all this stuff. Until we know at least a reasonable number of the tests, it's not, I don't think it's that productive to have you guys try to wade through it. But we will get to a point where we'll do a lot of them. What I was going to do now, I was going to kind of ask you guys something. So you took statistics, and I'm trying to teach a little statistics in my math for the liberal arts class. So I've been reading a statistics book. I started in the summer, and I bought a book on Amazon for like $3. It was an old edition. It wasn't the one that you guys used. It was another one that seemed to be fairly popular. Then Mr. Watkins told me the other day that nobody likes that book. So I got Mr. Appel's book, the one that you guys used, and I was looking at that as well. But what I've been trying to do is, reading the book, I've been trying to think about ways to use Excel to kind of explain the concepts of statistics. So you've already had statistics, and I thought maybe you could provide some insight or remembrance. I know it's hard. You might not remember anything about statistics, but so this relates to ultimately to the hypothesis testing. So what do you remember about hypothesis testing? Summarize Graham, what is hypothesis testing? Can you? Yeah, good. Go. How about you, Kelly? Pass. Evan, you're my only hope here. Yeah. Did you get? So there was in the book I've read about. There's lots of hypothesis testing, but the main ones, the first ones you start with is you want to know whether a sample. Well, you've got some new population, I guess you would call it, a new population of under some new circumstances, and you want to know whether that's different than the old mean. So what you do is you calculate the mean for the sample, and then you calculate the standard deviation for the sample. Well, ideally you'd know the standard deviation of the original population. That's where you use z-score, right? But if you don't know the standard deviation of the original population, that is a large number of data points, then you use the student t-score. Right? Do you remember that part? Okay. So, and I really, my first question about this whole thing was, what is if you take a population and you take a sample from that population of a certain size, the question is, how accurate is that sample estimate reflecting the population? That's the whole idea of estimation. Okay, remember that? You said confidence intervals. If you run an experiment and you get a mean and a standard deviation, and you've run 25 tests, how accurate is that mean? How confident are you of that mean being the population mean, the sample mean being the population mean? So I'm going to show you something. what I'm trying to do is see if you guys understand this, because if you don't understand it, then there's no way these other guys are going to understand. So I understand it, and I'm trying to get to a point where somebody understands it. So this is my, I'm trying to demonstrate these things, what I think, and there's a lot of stuff here, so bear with me. Okay. So what I did, what I did is in Excel you can generate random numbers, and you can also generate a standard normal distribution. So what I did was I used Excel to create a population of 1,000, because that seems like a pretty decent population of numbers. And that's what I have in this column here. I have a column of 1,000 numbers, and they are random number. They are a normal distribution with a mean of 50 and a standard deviation of I think 3. So they should vary between 44, mostly 44, and 56, plus or minus 2 standard deviations. And you can see the numbers, they are between 54 and 56, most of them. So that's my population. Now, when you run an experiment, what you're doing is you are essentially randomly picking a fixed number of those 1,000 samples, and that's your sample. And every time you redo your experiment, you're going to get 25, in this case 25 new data values. So your initial population is perfectly normal distribution. And so what I did was I created a histogram of the population. So that's the blue. And if you remember with histograms, what you're looking for. So So if you're trying to answer the question, Maya, if your sample is normally distributed, how did you guys determine that? Did you just look at the curve and say, yeah, that looks kind of like a bell, or did you come up with an actual number that reflected that? You don't remember? Does anybody remember? Okay. So normally you have to make a decision whether you think the data that you're sampling from is normally distributed. And what you look for is a bell shape. Is it bell shaped? And if you look at the blue curve, you can see the population is nice and it's a bell-shaped curve. So I would say the blue curve, which it should be because I made it that way. I made Excel to give me a randomly distributed set of numbers that were normally distributed around an average of 50. So it should be pretty symmetric. It's not quite symmetric, but it's pretty symmetric. Now the brown curve is the histogram from my sample. So then I came up with this way of picking 25 of these numbers randomly. So if I went through my 1,000 set of numbers, this would be one of them, and this would be another one. But these are all, again, picked randomly. So this is like a random sample. Because when you do an experiment, if you do your sampling correctly, the sample should be random. So these numbers were randomly picked from here. I don't know if I ordered them, I could find them easily, but right now they're not ordered, so I can't really. And then what I did is I did a histogram of those 25 randomly selected points. And so this is my histogram for that. So this is the sample distribution. The blue is the population distribution, which is normal. The sample distribution looks, you've only got 4 bars instead of how many? 1, 2, 3, 4, 5, 6, 7, 8. Does it look normal? Would I say is the brown data normal? Well, sort of. I mean, it doesn't have this nice perfect bell shape, but it has, you come from something really low and then you move up to somewhere it gets high and then it comes back down again. So the cool part about this is that every time I push F9, hopefully it does it today,